Good morning. So I would like to tell you about a paper that just got published a few days ago. A demonstration of an algorithmic quantum speedup is how we called it. And for the purposes of this event, I guess I should call it a NISQ-ish algorithmic quantum speedup. And I'll try to explain to you exactly what all that means. The work was done with my former grad student, Bibek Pokorel, who now works for IBM. Okay, so there are a lot of words in this title that need very careful explaining and defining. And I'm going to try to take you through how I think about quantum speedups, NISQ-ish speedups, and so on. So let's start nice and easy. First of all, what is a quantum speedup? Well, of course, to define that properly, we need some kind of a metric. And the metric that I like to use a lot and I think is quite useful for our purposes is the so-called time to solution metric. And it's extremely intuitive. The time to solution for a problem of size n and a circuit that takes you tr, that is the runtime of one iteration of the circuit, is simply the time it takes you to run the circuit divided by the probability to solve a problem of a given size n, right? So if the probability is 1, if you always succeed, then it just takes you one time to run the circuit. And if the probability is less than 1, then you're going to have to repeat it on average a few times until you find the right answer. So that's the time to solution. There's actually a more precise definition, which is a worst case definition that is the one we actually used in the paper, but for our purposes, this intuitive average time to solution definition is good enough. Okay, so let's use this to define a quantum speedup. And of course, to this audience, I don't have to tell anyone that a quantum speedup is not a constant factor like 100 times better or something. Of course, that's not what we mean. What we do mean is something that has to do with scaling. So a quantum speedup is a quantum advantage relative to classical computing in the time to solution that grows as a function of the problem size, right? And so typical examples, we all love exponential speedups. So imagine that the quantum time to solution is polynomial in the problem size. Classical is exponential. That would be an example of an exponential quantum speedup. You could have a polynomial speedup when the quantum algorithm has a lower degree polynomial than the classical algorithm. And you can also have a polynomial speedup if the quantum and the classical times to solution are both exponential, but the quantum exponential is lower than the classical, right? So if you try to express one in terms of the other, then that's a polynomial speedup. And this actually is the context for much of this work. So what is a quantum speedup? It's an advantage in the scaling of the time to solution with the problem size. And because this is NISQ, I want to say something that is perhaps slightly controversial here. I would say that we have a quantum speedup even if the classical time to solution is overall smaller. Because what we care about is scaling. Okay? So scaling, that's the key. Okay, so now the title of the talk is about an algorithmic quantum speedup. So let me add algorithmic here. So what's an algorithmic quantum speedup? Well, it's the case when you can solve some computational problem, and we can define exactly what we mean by that, by running a quantum algorithm on a quantum computer and demonstrating a quantum speedup quantified in terms of the time to solution over the best possible classical algorithm. Okay, so caveats. Okay, so first of all, the notion of a quantum speedup on a NISQ device. What do we mean by that? Well, today's quantum computers have small numbers of qubits. So how do we know that the speedup isn't just a finite size effect, right? So imagine that this is time to solution as a function of problem size. And imagine that in reality, this is what's going on, right? The quantum time to solution starts nice and small, nice small slope compared to the classical time to solution. But it could be that we're just somewhere in this lower corner down here because our quantum computers are small. And that if we were to go to large enough sizes, we would find that the quantum time to solution actually becomes worse, both in scaling and in total time. Right? And so how can we rule this out on our current devices? And I'm afraid the answer is that we can't. All we can do is we can extrapolate. So in other words, let's say we're here, and we can extrapolate and hope for the best in some sense, experimentally speaking. And then we can try again when we have a larger computer. Unfortunately, larger and larger computers are coming online all the time. So this is definitely doable. But the one thing I will insist on is that the speedup, if we make a speedup claim, a scaling speedup claim, then it must persist up to the largest number of qubits that is compatible with whatever generation of the current quantum computer is that you're using. Okay, so if your quantum computer is of a size that allows you to go up to here, great. But if it allows you to go up to here and you're starting to see that, or up to here rather, and you're starting to see that the classical scaling is better than the quantum scaling, then don't stop here when you can go all the way to here. That wouldn't be fair. Okay, so now about best possible classical algorithm. How do we know that? Well, okay, so here, of course, computer science guarantees come in, and they're very useful. But even then, often we don't know what the best classical algorithm is. In the best case scenario, we'll have proofs. And actually, the case that I'll talk about today will have a proof. But typically, we don't have proofs. And all we have is some kind of best available classical algorithm. And that's another fact of life. So another caveat in the definition. OK, so now I want to add one more adjective, unambiguous algorithmic quantum speedup. And the only change in the definition is the addition of without any conjectures or assumptions. And I want to emphasize this case because we might ask, do we currently already have examples of unambiguous quantum speedups using current quantum hardware? And the place to look, forgive me if I left something important off this list, I would say that we want to look at the cases of quantum supremacy, quantum machine learning, quantum simulation, and quantum optimization. This is where most of the focus has been. And I think it's fair to ask whether we have, within the context of these four settings, whether we have examples of unambiguous quantum speedups. And here's where I'll probably offend a lot of people. I would like to claim that despite the fantastic progress we have in these areas, we don't yet currently have examples of unambiguous quantum speedups in these four categories. So the quantum supremacy and the quantum machine learning demonstrations, and I've listed representative references, they are definitely extremely interesting, but they still rely on reasonable but unproven computational complexity conjectures. Right? Now, these conjectures are extremely credible, but they are still at the level of conjectures. And in the quantum simulation and quantum optimization cases, the advantage is against best available, not best possible classical algorithms. Right? So this is the context of quantum simulation, and in a recent experiment by D-Wave, for example, as well as a recent work on max set using Rydberg atoms. So these are benchmarked against best available, best currently known classical algorithms. That's the context for the speedup there. So in our work, our goal was to demonstrate this unambiguous quantum speedup. And of course, to do that, we have to make some other sacrifice. Right? And so the sacrifice we make in order to get into unambiguous territory is to assume the setting of an oracle. Okay, so the one thing I can say about, I'll have a lot to say about the oracle, but I will say that we are pricing in the resource cost, that is the time it takes you to run and the time it takes you to construct the oracle. Okay, so what is this oracular algorithm that we're working with? And you all studied it in your early phases of your quantum computing careers, undoubtedly. This will be the setting of the Bernstein-Vazirani algorithm and problem. And by the way, despite numerous searches, I've never been able to find a picture of Ethan Bernstein. If anybody has a picture of him, please send it to me. The Bernstein-Vazirani algorithm is essentially the context for a game where you have to guess a secret bit string of n bits. And so let me describe it in some detail, and also the modification that we apply to this algorithm to make the problem, not to the algorithm, the modification to the problem in order to make it harder. So you have access to an oracle, and the oracle knows the secret string b, and you can feed your guess x to the oracle, and the oracle gives you back b dot x mod 2. So that is just the sum mod 2 of the bitwise products between the secret string and your guess. So the one modification that we make to the original setting is that rather than the oracle keeping the same fixed bit string b, it changes after every time you make a guess. So you're only allowed one guess. So after you make your guess, then you get to guess the entire bit string based on the information that you received. And you win if you guess the correct string. After your first initial guess, you lose otherwise. And then a new secret string is selected by the oracle, and the game starts again. So let's analyze this. It's a very simple problem to analyze. So for example, suppose you try the 1 and then all zeros bit string. Then the inner product is just the first bit. All right? So in fact, no matter what you do, you'll only get one bit back, because b dot x mod 2 is just one bit. And you can easily convince yourself that there's really nothing more than you can do, well, nothing more you can do than to just get one bit like the first bit. So that means that no matter what you do classically, n minus 1 unknown bits remain. And therefore, the probability that you'll successfully guess b is just 1 over 2 to the n minus 1. Okay, so let's calculate the time to solution. The time to solution, remember, the numerator is the time it takes to run the algorithm. The time it takes to run the oracle is n, because it takes time n to add the bits. So the time to solution, on average, it will take you n times 2 to the n minus 1 attempts before you correctly identify a secret string b. That's it. That's the classical complexity of this problem. So here's a little classical reversible circuit that demonstrates this. You start with your guess here. You add an extra ancilla. And suppose that the secret string is the all ones string. Well, it turns out that the rule for constructing the oracle is wherever there is a 1 on bit I, you do a control knot between I and the ancilla. So there are control knots from every bit here to the ancilla. You add up all the results, and that will give you the inner product as needed. And so you see that in the worst case, that's this all one string. It takes time n to run the oracle. That's why I had an n in the numerator of the time to solution. So now you pick a new b. For example, let's say the first bit is now 0. So I cancel the first control knot here, and so on and so on. And you see that in the classical case, only the ancilla contains useful information. Right? The other bits just get copied over. OK, so now we get to the quantum Bernstein-Vazirani algorithm. That's a textbook example. Here's the circuit. It starts with Hadamard's and the ancilla in the one state. Then the oracle. The oracle is the identical oracle to the classical oracle. But of course, it acts on quantum states now. And then more Hadamard's. And then you read out all the data qubits. And in this case, all the data qubits contain useful information. They reveal, in this case, the secret string. So you can prove, Bernstein-Vazirani did this 30 years ago, that this circuit returns the correct string with probability 1. And so the time to solution is n for the quantum circuit, because it still takes you time n to run the oracle, versus the classical n times 2 to the n minus 1. Right, and I just want to highlight that the original standard, the original Bernstein-Vazirani problem was not a single-shot problem. It was a problem where you kept the secret string fixed. And in that case, you can solve the problem classically in just n oracle queries, because every time you get another bit. All right, so in that case, the classical time to solution is n times n, again, n to run the oracle, n squared versus quantum n. So you would get a linear quantum speedup, not an exponential speedup. This is all assuming ideal quantum circuits. OK, so let's look at the ratio, the speedup ratio, just to make things very explicit. The classical time to solution versus the quantum time to solution. Here are the formulas. And of course, the ratio is 2 to the n minus 1. That's the quantum advantage in this case. But so far, I've assumed that everything is ideal. OK, so now let's say that we're talking about noisy circuits, which of course we are in the NISQ era. And let me take the simplest, most basic back-of-the-envelope model for the noise, and that will suffice for our purposes here. Let's assume that every gate and measurement is imperfect, and therefore the fidelities multiply. And let's just say that there is a single number lambda that characterizes the effects of noise and decoherence. And so if you have a circuit of depth n, which is what you do in terms of the oracle, then the success probability will not be 1 in the quantum case. It will be exponentially small. Right? So let's say it's 2 to the minus lambda n. That's what we might expect in the most naive analysis. So how does that modify things? Well, in terms of the time to solution, let's recompute the speedup ratio. So now this 1 has become a 2 to the minus lambda n. And so the speedup ratio is this. Okay, or if you'd like to express the quantum time to solution in terms of the classical time to solution, there's this power of lambda here now. Right? And so you get a quantum, that's why I'm calling it a polynomial speedup, whenever lambda is less than 1. Right? So the quantum advantage is manifested whenever lambda is less than 1. And this lambda less than 1 is the one thing you should remember when we start to look at data. Lambda is essentially the slope on a log-log plot of the time to solution. All right, so that's it. That's the full extent of the theory that we need here. So now let's go to experiments. And we implemented this single-shot Bernstein-Vazirani algorithm on 2 different IBM machines. These are 27-qubit IBM machines, Montreal and Cairo. So here is the graph. And there's a lot of data IBM supplies, and I don't want to bore you with a big table. I just want to highlight a couple of things here. So the 2-qubit gate error and the readout duration. So for Montreal, the 2-qubit gate error reported back when we did the experiments was 1.35%, and the Cairo 2-qubit gate error was roughly 3 times bigger. Okay, so or 4 times bigger. So Cairo is a noisier machine in terms of its 2-qubit gates. And the readout duration, on the other hand, is significantly longer for Montreal. So we expect there to be some trade-offs. We expect that overall the fidelity of Montreal will be higher, but it's going to take longer to get results on Montreal. And this roughly corresponds also to the reported quantum volumes. OK, so let's look at results. So first, let's fix n. Let's set n equals to 6. So we're talking about 6-bit strings here. And for 6-bit strings, there are 2 to the 6, 64 possible secret strings, or 64 possible oracles. And so what you're seeing here is the experimental data that we got sorted. Oracle number, or secret string number, sorted by Hamming weight, versus the actual detected state. Again, sorted by Hamming weight. And if everything were perfect, then everything would be perfectly on the diagonal. And this is the color is the success probability. So dark is high success probability, and orange is low success probability. And a very clear pattern immediately emerges. The low Hamming weight bit strings are found with high success probability correctly, and the high Hamming weight are more erroneous. And you see there's some off-diagonal scatter here, which are the incorrectly identified secret strings. So we can interpret this data. Again, most of the errors are at higher Hamming weight, and that just means that we have more controlled knots. Right? More ones means more controlled knots, if you remember how the circuit is put together. So that's consistent with higher depth circuits suffering more decoherence. And that's why the success probability is lower here. Now, if you average the success probability over all 64 possible bit strings, you find that the quantum success probability here is already 72%, which is not bad, considering that the classical success probability in this case would be 2 to the minus 6 minus 1. That's only 3%. So you might ask, well, is this evidence of a quantum advantage? Right? This is a pretty good result. But remember that, at least according to my definitions, we want to look at scaling and not at fixed n. And so is this sufficient for quantum speedup? And the answer is a resounding no. And let me try to explain this busy graph to you that answers the question. And so this is the time to solution versus the length of the bit string. And first of all, I hope you can see these white grid lines in the background. So the white grid lines are simply the classical scaling for this problem. So time to solution is n times 2 to the n minus 1. Right? So the slope of these lines tells you the classical scaling. And if you were to run the problem on a good CPU you can buy from any vendor, let's say with a 10 gigahertz clock speed, then the classical line would be here. So the dashed lines here are the ideal quantum scaling, so that is n if we had a perfect quantum computer. Blue is Cairo, which remember had a shorter readout time, so it starts out smaller. And orange is Montreal. So this would have been the ideal quantum computer performance. And this is reality, the data here. And you see that reality is not so kind because for both of these machines, lambda is greater than 1. Right? And we measure lambda by looking at the largest sizes that we were able to run on these devices and just computing the slope. And so very clearly the slope here is worse than classical, so we have a quantum slowdown. Actually, it's even worse than a quantum slowdown. We have a quantum blowup. Because as it turns out, at least within the 10,000 shots that we gave every problem size for every bit string, on Montreal, the solution, the correct bit string, was never found beyond size, 16, I think. And likewise, on Cairo, the correct bit string was never found for sizes larger than 19 or so. Okay, so far not good. Classical 1, quantum 0 in this game.
So the example you showed on the last slide was n equals 6?
Yeah, that's right. So n equals 6 is here. And since you asked if you were to stop at n equals 6 and you were to compute the slope, you might conclude that things are looking pretty good. But it's important to keep going until the largest size available. Okay, so what do we do? Well, we already heard from Alex yesterday about dynamical decoupling. And let me briefly remind you what this is. So dynamical decoupling is an open loop quantum control technique, which we will put to use to try to rectify the situation here. So basically, dynamical decoupling you can think of as applying pulses at some intervals. And let's try to make the pulses as narrow and strong as possible. And you get to choose which type of pulse, so an X, a Y, whatever, and you get to choose the intervals. And in the simplest version of dynamical decoupling, spin echo, you choose the pulses so that they time reverse the unwanted interactions. So here's a simple explanation of this. So suppose we have a system bath Hamiltonian, and we can choose a pulse p such that this identity holds. Puts a minus sign. in front of the system bath Hamiltonian. And let's denote the free evolution, so these are the intervals between the pulses here, by f sub tau. Okay, so now consider this calculation here, a free evolution followed by pulse, followed by free evolution, followed by pulse. So now you can lift the p and the p dagger upstairs. And because I assume that the p's have the effect of flipping the sign, this minus sign becomes a plus. And they cancel, and you get identity, right? So it's like going forward, going backward, ending up in the same place. That is the simplest version of dynamical decoupling. And this is not fiction. For example, suppose you have a pure dephasing type coupling to the bath. So system bath interaction has z, sigma z on the system. Well, because x anti-commutes with z, it does precisely what we want. It puts a minus sign in front of the interaction. And so in this example of pure dephasing, you would apply a bit flip, a pi pulse along x in order to remove or suppress the dephasing. And that holds to first order in the Manx expansion. Higher orders are more complicated to deal with. But to first order, this is correct. Now, it's not limited to removing dephasing. In fact, any system bath interaction can be suppressed by an appropriately chosen set of dynamically coupling pulses. And to illustrate that, for a single qubit, the most general system bath interaction you can write down looks like this. And it's easy to convince yourself that if you were to apply the so-called XY4 sequence, which is at least 50 years old, if not more like maybe 70 years old, you will achieve the same effect as what's shown here. So this is enough. This XY4 sequence, which is X, Y, X, Y, will, to first order in the Magnus expansion, completely cancel an arbitrary single qubit interaction. And this can be done for any system bath interaction. OK, so we actually tried this several years ago on IBM machines. Here is the fidelity for single qubits. So this is a single qubit experiment as a function of time. Without dynamical decoupling is the black data, and with dynamical decoupling is the red data. So you get a factor of 6 improvement in the fidelity decay time. And this is for one of the older Rigetti machines from the same paper in 2018. There the improvement was a factor of 2.5. Now, the XY4 sequence is good, but we know that there are much better sequences out there. So there are sequences that exhibit robustness to pulse imperfections, and there are sequences that cancel beyond first order Magnus. So there's a paper here where we studied a lot of these sequences on IBM machines, and you might want to check it out. But I want to focus on one particular sequence which was discovered by Genov et al. And this is the so-called universally robust sequence, indexed by n, which is not the number of qubits. This is good for a single qubit. And I'm not going to go into detail. Ask me about it later. There's a family of these sequences, and exactly how they work is somewhat intricate. But let me just show you some data to show you that as you increase the order of this URN, n is now the order of a sequence, the number of pulses essentially, things get really good. So here is from this paper, data for the fidelity as a function of time, trying to preserve the state of a qubit with, well, free evolution is the orange data here, and XY4 is blue, and CPMG is dark blue, and then this UR order 20 sequence, the data looks beautiful. Right? So this is a really good sequence. And just to give you a slight intuition about how it works pictorially, here's what happens if you try to run XY4 with imperfect pulses, pulses that have 15 degrees over rotation and 5-degree axis angle errors. And with XY4, you were supposed to go back to where you started, but you end up down here. And with the UR6 sequence, which uses 2 more pulses than XY4, you make this complicated trajectory, and at the end of the day, you end up almost precisely where you started. And that's just the order 6 sequence. So we did an exhaustive search over the space of URN sequences and found that UR14 was optimal for Montreal, UR18 was optimal for Cairo. So those are actually the sequences for the data that I'm about to show you next. Okay, so here's the abstract Bernstein-Vazirani circuit. Here's what happens when we insert the dynamical decoupling pulses. How do we combine dynamical decoupling with running an algorithm? The way we do it is we just look for the gaps, the idle times in the circuit. So here's a long gap on the first qubit, and we insert a DD sequence there, schematically shown with 4 pulses. But as I said, it was actually 14 or 18 for the two different machines. Or here on qubit 2, there are 2 gaps. Right? So we insert a DD sequence here and another one here. And this is possible because the control knot takes much longer than the Hadamards. Okay, so that's the scheme for how to combine DD with computation. Okay, so what happens when we do this? Well, this is the data that I already discussed on the left without doing dynamical decoupling. With dynamical decoupling, specifically with the UR18 sequence on Cairo, things get quite a bit better, right? So especially in the high Hamming weight corner down here, things look a lot greener. And the average success probability has gone up from 72% to 80%. So now you ask the same question, right? Is this sufficient for a quantum speedup? This is a fixed size, 6. Do we now get a speedup? Well, that's the data that I already showed you, where things were not looking good. But if we add dynamical decoupling, there are 2 new curves here. For Cairo, things got much better, but not quite there yet. Right, so this is the same experiment repeated with dynamical decoupling inserted. And now the slope is just under 1. But with 2 sigma error bars, it is not sufficient to claim that we have a speedup. However, for Montreal, at least up to the largest possible size, which is 26, this is a 27-qubit device, and 1 qubit is used as an ancilla, the slope is 0.6 plus or minus 0.03. Again, 2 sigma error bars here. So that's the speedup that I advertised. Okay, and if this were Shor's algorithm, then we would all be out celebrating. But it's Bernstein-Vazirani, so we've got to start small. But this is the signature. Still, I have to put this on ice. If you were to run this on a really decent CPU, in terms of the absolute time to solution, that's the curve. So you would still lose dramatically to a classical computer. Right. But in terms of scaling, the situation is now good. Now you might play the game of, well, let's imagine that we had a smaller quantum computer. Right? So let's look at the scaling for smaller sizes, even though we don't have to. And so this is the slope measured from 3 up to n qubits, where n goes up to 26. Right? And so the slope in the green zone here is when we have a speedup. The slope is less than 1. In the red zone, we lose the speedup. And without dynamical decoupling, you see how you could have easily fooled yourself into believing that you have a speedup up to around here, n equals 14 or so. Right? So if our devices were too small and we were to run this experiment, we could have claimed a speedup by stopping here. But fortunately, these devices are large enough to rule this out. And you see that the slope actually becomes larger than 1, no speedup. That's without dynamical decoupling. Now, with dynamical decoupling, the reason we don't want to claim a speedup on Cairo is because you see how the slope picks up. And it's easy to imagine that if we could only go a little further, then we'd get into the red zone. But on Montreal, at least up to the largest available size, the slope is clearly and firmly in the speedup territory. Okay, so how about larger sizes? I'm almost done. We ran this on the Falcon technology, processor technology with 27 qubits. We tried it with the larger devices, but I have to say, my complaints to IBM management did not help here. The job's never finished. They're still running. I don't know what's going on there. Maybe if I talk to the VIPs in the audience here, things will move along. We're also trying this with Rigetti. They have an 80-qubit QPU. That's still a work in progress, so I have no results to report, but we're working on it. And so to conclude, we defined a problem, the single-shot Bernstein-Vazirani, with a provable quantum speedup that is free of any conjectures, right? And we implemented it on current quantum hardware. And this was sufficient to demonstrate an unambiguous quantum speedup on one of the two machines that we tried. The speedup was possible thanks to the application of dynamical decoupling, an error suppression method. And it was not possible without dynamical decoupling, so this highlights the importance of doing error suppression. And currently, we are working on larger problems with newer chips. We're working on optimizing the dynamical decoupling because much better results can be squeezed out of these machines with more work. We're also looking at other algorithms. Stay tuned. And I want to thank you, and especially Bibik, who did all the hard work.